Chapter 21, Molecular Orbital Theory, Section 21.9, the Hückel Method. The Hückel Method can be used to predict the molecular orbital energies and resonance energies of conjugated cyclic and acyclic polyions. For example, we can use the Hückel method to calculate the molecular orbital energies for 1,3-butadiene. 1,3-butadiene contains 4 carbon atoms, each contributing a 2p orbital and a 2p electron to form the conjugated system. The Hückel method involves solving this equation for 1,3-butadiene. On the left hand side, we have a 4x4 determinant because over here we have 4 MOs. Each consists of some contributions from the 4 2p atomic orbitals. And H sub ii are called Coulomb integrals. Hi different from J are called resonance integrals. S sub ij is the so-called overlap integral. For simplicity, we're just assuming S sub ii is 1 and S sub I different from J is just 0. This is the approximation for us to use to solve this determinant. We also set H sub ii to be alpha, Hij to be beta, when I and J are different. Both alpha and beta are negative. For most polyions, beta is around 10% of alpha, and alpha is simply the 2p atomic orbital energy of carbon. We can look up this value. It's roughly negative 11 electron volts, or negative 1,100 kilojoule per mole. Now let's look at this Hückel method. We can expand this 2x2, 4x4 determinant in this form. So over here we have diagonal terms. We have Hii minus epsilon Sii as alpha minus epsilon. It's just because Hii is alpha, H11 is alpha, H22 is alpha, H33 is alpha, H44 is alpha. And then minus epsilon times S11, epsilon times S22, epsilon times S33, epsilon times S44. And again, S11 is 1, S22, S33, S44, they are all 1. So that's why we have diagonal terms like this. Now beta. When I and J are different, we have a beta here. But why is this 0? Because this carbon is adjacent to this carbon. There's a resonance integral between these two neighboring carbon atoms. However, between carbon 1 and carbon 3, there's no resonance integral. Between carbon 1 and carbon 4, there's no resonance integral. That's why you put 2 zeros here. Now let's look at carbon 2. Over here, this is H22. And on the left hand side, you have beta. On the right side, you have beta because carbon 2 is bonded to both carbon 1 and carbon 3. That's why you see beta on the left and right hand side. Now let's look at carbon 3. Okay, this is carbon 3. Alpha minus epsilon, which is H33 minus epsilon times S33. And also you have a beta on the left, a beta on the right. Because this carbon 3 has carbon 2 on the left, carbon 3 on the right. Therefore, you have 2 resonance integrals in this row, one on the left, one on the right. Finally, carbon 4. When we look at carbon 4, well, there's only 1 carbon on the left, so therefore we have only 1 beta in this 4th row. And over here we have a 4x4 determinant. We need to expand this determinant and solve the equation. There's a systematic way to expand determinants. So you can use this term, alpha minus epsilon, multiplied by a 3x3 determinant. And then this beta multiplied by also a 3x3 determinant. That consists of 1, 2, 3 elements here, 3 elements here, and 3 elements here. And when you look at the second row, you need to change sign. So it's really negative beta times a determinant with the first column as beta 0, 0, second column as beta alpha minus epsilon beta. The third column should be 0 beta times 0 beta and alpha minus epsilon. And then plus 0 times another determinant. Anyway, 0 times the determinant is just 0. This 0 times the determinant is 0. So we can expand this 4x4 determinant and we get this kind of expression. This is the 4th order polynomial function of epsilon. We're going to solve this polynomial equation. Using the Hückel method, again, we can assume Sii is just 1, Sij is just 0, and we set Hii is alpha, Hij is beta, if I and J are adjacent to each other. Again, over here, alpha is simply the 2p atomic orbital energy of carbon, roughly negative 11 electron volts, or negative 1100 kilojoule per mole. Beta is the so-called resonance integral. This beta contributes to the pi bonding energy, and later you'll see also resonance energy. We do have to solve this 4x4 determinant. I talked about how to set up this 4x4 determinant. In the diagonal term, you just have alpha minus epsilon for the diagonal term, and then you need to examine the situation for every single carbon. So carbon 1 is bonded only to carbon 2, so you just put beta here, and then 0 here, 0 here. Carbon 2 is bonded to both carbon 1 and carbon 3. That's why you have 2 betas on the left and on the right. Carbon 3 also is bonded to 2 carbon atoms, carbon 2 and carbon 4. That's why you have 2 betas here in this row. And carbon 4 is bonded to only carbon 3. That's why you see only 1 beta. We can expand this 4x4 determinant, so we get this polynomial equation, and then we can somehow simplify this polynomial function. We get this. Now, how do we solve this? One way is to do variable substitution. If we set x to be alpha minus e squared, we'll simplify this fourth order polynomial equation to just a quadratic function. We'll solve this x. How do we solve x? Well, it's just pretty simple. I think we just need to use negative b plus minus the square root of b squared minus 4ac over 2. That's over 2a. That's just the standard solutions to quadratic equations such as ax squared minus b, plus bx plus c equals 0. So we get this kind of solutions in terms of beta squared. We have 2.6 beta squared. We have 0.38 beta squared. And now alpha minus e is simply the square root of this, or the square root of this. And therefore we solve for alpha minus e to be plus minus 1.6 beta, or plus minus 0.6 beta. Why do we have 4 different solutions? Well, this is a fourth order polynomial equation. That's why we have 4 different roots or solutions. The 4 MO energy levels of butadiene are determined to be epsilon equals alpha plus 1.6 beta, alpha plus 0.6 beta, alpha minus 0.6 beta, alpha minus 1.6 beta. Remember, both alpha and beta are negative. Alpha is negative 11 electron volts. Beta is usually 10% of alpha, so all those are negative. And the 4 pi electrons should occupy the 2 lowest energy levels. So I would say these 2 energy levels with more negative energy. The total energy of this 4 pi electrons is going to be 2 times this energy and 2 times this energy. Altogether, you get 4 alpha plus 4.472 beta. Now let's look at the resonance energy. The resonance energy is the total energy of this 4 pi electrons in resonance over here, minus, well, over here 4 alpha plus 4 beta are the total energy of 2 separated double bonds, and the difference is 0.472 beta, and this is the resonance energy in 1,3-butadiene. Again, 4 alpha plus 4 beta is the energy of the 4 pi electrons of 2 separated pi bonds. How do we compute the bonding energy or molecular orbital energy for ethane? Well, ethane contains only 2 carbon atoms, so we can write a 2x2 determinant this way, and we solve this equation. We get epsilon is equal to alpha plus beta, epsilon is alpha minus beta. So for the ethane molecule, the 2 pi electrons should occupy this energy level. The total energy would be 2 alpha plus 2 beta. Now, what if you have a molecule that contains 2 separated double bonds, unconjugated, and then, well, for each double bond you have this much energy, and for the second double bond you have this much energy. Therefore the total is 4 alpha plus 4 beta. Again, get back to 1,3-butadiene. The total energy of the 4 pi electrons is 4 alpha plus 4.472 beta. So we can take the difference. We get the resonance energy for 1,3-butadiene, which is roughly 0.5 beta. Using the Hückel method, we can also demonstrate that this cyclopropenenyl cation C3H3 plus is aromatic. And we can again look at the structure over here. We have carbon 303 forming a ring structure. We have a plus charge on the entire molecule, and this plus charge is delocalized over the entire molecule. Now let's write out a 3x3 determinant, because we have only 3 carbon atoms, each contributing 1 2p atomic orbital. So 3 2p orbitals will make 3 MOs. Since we make 3 MOs, we need a 3x3 determinant to determine the molecular orbital energies for the 3 MOs. So again, the diagonal term has to be alpha minus epsilon, all 3 diagonal elements, and then off diagonal elements, it's beta beta here, beta beta here, beta beta here. Why 2 betas in the first row? Because carbon 1 is bonded to carbon 2 and also carbon 3. That's why you see 2 betas here. This is a ring structure. This is a ring structure, and that's why each carbon is bonded to 2 carbon atoms, and therefore you need 2 betas in this every single row. Solving this equation, it's doable. I mean, it's just a 3x3 determinant, so you can use this term times this term times this term, and then you can use beta times this beta, and then finally beta times this beta. You get 3 positive terms. And you also have 3 negative terms, which is this beta times this. That should be negative, and then beta times this, and should be negative, and also beta times alpha minus epsilon. That's also a negative term. So you combine 3 positive terms, 3 negative terms. You combine everything, you get one single third order polynomial equation. Set it to 0. We solve it. We get 3 roots. It's going to be alpha plus 2 beta, and then alpha minus beta, and alpha minus beta. So this 2 means we have degenerate molecular orbitals. Alright, 2 molecular orbitals with the same energy. Now if you look at this structure, we are carbon 3H3 plus. That means we have only 2 pi electrons. So these 2 pi electrons will occupy this MO, the lowest energy MO, and the total energy will be this times 2, which is 2 alpha plus 2 beta, 4 beta. So this alpha plus 2 beta multiplied by 2, we get 2 alpha plus 4 beta. Now let's consider just a isolated carbon-carbon bond. What's the molecular orbital energy? It's just 2 alpha plus 2 beta. So compare this and this, you can see over here we have 4 beta, here we have only 2 beta. The difference is 2 beta. We have a lot resonance energy in this structure. It's 2 beta. The value is 2 beta. It's larger than 0.5 beta for 1,3-butadiene, and therefore this ring structure of carbon 303 plus is a aromatic structure. Now finally, let's look at benzene. When you look at benzene, there are 6 carbon atoms. Each carbon atom contributes 1 2p atomic orbital, and we have a total of 6 2p atomic orbitals forming 6 MOs. So you're looking at the 6 MOs here, the lowest energy MO, second lowest energy MO with a degeneracy of 2, and then these 3 are kind of just anti-bonding pi orbitals, and these 2 MOs are also degenerate. Finally, we have the highest energy MO over here. Now if you look at the number of nodes that cut through the benzene ring, zero nodes over here. We have a node that cut through this benzene ring, 1 node here, or over here also 1 node. This is just vertical, this is a horizontal node. And over here there are 2 nodes, 1 2. There are 2 nodes. Over here 2 nodes, 1 2. And over here we have 3 nodes, 1 2 3. So as the number of nodes increases, the energy of the molecular orbital also increases. Now let's look at this 6x6 determinant. Just because we have 6 MOs formed from 6 conjugated p orbitals, we need to solve this 6x6 determinant. We set it to 0. Now the diagonal elements are all alpha minus epsilon. But now this is carbon 1. Carbon 1 is bonded to carbon 2 and also carbon 6. That's why you see 2 betas in this row. And now carbon 2 is bonded to carbon 1 and carbon 3. etc. Finally, this is carbon 6. Carbon 6 is bonded to carbon 5 over here. It's also bonded to carbon 1. So that's why you also see 2 betas in the last row as well. So this is a ring structure. That's why each carbon is surrounded. It's bonded to 2 neighboring carbon atoms. Now we just solve this. How do we decompose a 6 by 6 determinant? Well, it's non-trivial. I'm not going to show you every single step. I would use a program. I would write a simple computer program to solve this, and I'll just tell you what the solutions are. So over here we have energy alpha plus 2 beta, alpha plus beta, alpha plus beta. This is alpha minus beta over here, alpha minus 2 betas. Alright, remember alpha and beta are both negative. For carbon, alpha is roughly negative 1100 kilojoule per mole, and beta is roughly 10% of alpha. That's why these 3 MOs have lower energy. Alright, and now we occupy those MOs with 6 electrons. And now let's look at the total energy. It's going to be 2 times alpha plus 2 beta, and then 2 times alpha plus beta, and then 2 times alpha plus beta. We get 6 alpha plus 8 beta. 6 alpha plus beta, 8 beta. And now let's consider 3 isolated carbon-carbon double bonds. Well, that would be 6 alpha plus 6 beta. Now we have 6 alpha plus 8 beta. What's the difference? The difference is 2 beta. So 2 beta, again, is the resonance energy of benzene. Benzene is an aromatic compound with significant resonance energy. And now if you look at similar structures, for carbon 4H4, a ring structure with 2 double bonds, you're going to get 4 MOs. You're going to get 4 MOs, but unfortunately in that case, you will not get any resonance energy. So actually carbon 4H4, the ring structure with 2 double bonds, is so-called anti-aromatic.